Okay, the next step in our process is to convert this double dabble algorithm that we did. We sketched all the stages that have to happen. We went through the calculations. We see why it works. But now we need to describe that in Verilog so that we can implement it in hardware. That's the nice thing about making a behavioral description. Okay, we're going to do this and we're going to see that we can describe this in a way that makes it easy for the tools to synthesize this into hardware. And in fact, it saves us a lot of work because this would be hard to visualize how this would work out as a schematic. Okay, so the first thing we do is we're going to set up some ports. Okay, so I have input ports, I have output ports. Okay, this is going to be an 8-bit case. I'm going to ask you to extend this to 14 bits. The reason 14 bits is because we have 4 decimal digits. The biggest number we can display is 9,999. So it takes 14 bits to represent 9,999. Okay, so I'm going to want you to extend it to 14 bits. All right, so this 8-bit case, the biggest number that we can have for 8 bits doesn't extend into the thousands. It stops at the hundreds. Okay, so you're going to have to, when you extend this to 14 bits, you're going to have to add a thousands place. So you do the same kind of definition, BCD thousands. And this would also be 4 bits, 3 down to 0. And it's just a regular output wire. Okay, so it turns out we're going to be using a behavioral description. And I've always told you if it's behavioral, all right, you need to use reges. But why did I use wires? Okay, well, it turns out we're going to use an internal shift register. Okay, so register is kind of a nebulous term. Think of it as a data type that can store things, okay, and help us connect things together in a behavioral description. All right, so this gives you the calculation on how big this should be for 8 bits. Okay, so I have to have 4 bits for the hundreds place, 4 bits for the tens place, 4 bits for the ones place, and then 8 bits for the number that I'm trying to convert. So that adds up to 20 bits. So if I was going to do 14, I would have the thousands bits, I'd have the hundreds bits, I'd have the tens bits and the ones bits, and then I have 14 other bits. So you can add all that up and you get the new size that you would need for your case for the shift register. Okay, so here's a new thing. All right, we are going to define a shift register, but it's going to be 2-dimensional indexing. Okay, so before we'd only had 1 dimension. So we talked about you can make something that's 19 down to 0, so that'd be 20 bits wide. But this time it's not only just 20 bits wide, there's also 9 of them. Okay, so they're indexed 0 through 8. All right, so if you go back to our diagram, we had an initial state, okay, so that would be where we had nothing shifted, so that would be stage 0, and then we went from 0 all the way through stage 7, and then the last stage we had a shift, okay, so we'll talk more about the numbering here in a second, okay. Next, another thing that's new is there's an integer I. It turns out we're going to use a for loop so that we can extend this and do this in stages. We have the ith stage connecting to the I plus 1 stage. So we'll sequence this in that way so that we don't have to write out every little stage that would show up in this algorithm. So the picture before, if you go back up here, I had 0 through 8 stages, right? 0 ending at 8. You would have had to have a set of code written for each one of these unless you use a for loop. And then you can do it in general, and that way it's easy to extend. So that's what we're going to be doing. Okay, so if you use, if you're extending to 14 bits, you'll have more than 8 stages. That's just a hint. You'll have to calculate how many of those would be. All right, so the next thing we do is we start our behavioral always block. Okay, so we have the sensitivity list. It's a combinational circuit, so we can do the star to say be sensitive to everything in here. All right, then we start with an initialization of shift register 0. So remember, shift register 0 for this 8-bit case, that's 20 bits wide, but this is the first one. It's initialized to binary. Binary is 8 bits. And then I have 12H000, so each of these would be 4 bits long, so 12 plus 8 is 20. All right, so that makes sense that that's the initial value of the shift register, 0. Okay, so the next thing we do is we're going to go through this in stages, 0 through 7, just like the diagram. And, we have this increment like you do in C where you can add 1 to I to make that increment. There's not an I++ in Verilog like you would see in C. So we just do I equal I plus 1. Okay, so if you go back to look at what we did, the first thing we did is we shifted. All right, so here's an operator in Verilog that says shift all the bits over to the left by 1. Okay, so that's what we're doing. We're saying our next stage, so if I is equal to 0, this would be stage 1. Our next stage is you just shift things over. All right, and so then from here, I want to draw circles around this in yellow. Okay, so in yellow, what we're doing is we are dabbling that hundreds place register. Then we dabble the tens place register. Then we dabble the ones place register. So remember what dabble was? You take the value of the register, you compare it. Let me get rid of this highlight so you can see it better. So you compare it to 5. All right, so this is a multiplexer notation. So you take, hey, here's this variable. I'm going to compare it. If it's greater than 5, it's going to be this value. Okay, if it's less than 5, it's going to be this value. Okay, that's that weird notation that I talked about in class for a multiplexer. So that's kind of cool, actually, because I can think of this as a mux. That's how it's going to be implemented in hardware. And all this notation is just showing what wires do you connect to that multiplexer. Another thing that I'm seeing here is there's a comparison here to 5. Later on, we're going to talk about building block circuits. One of those building block circuits is a comparator. So I see a comparison there. In my head, I'm thinking, oh, that's going to be another circuit that gets implemented by the tool to make this convert into hardware. Okay, so 3 different things here because we have 3 different 4-bit BCD registers that we have to keep track of. For the 8-bit case, we have the hundreds, we have the tens, and the ones. Okay, so if you're extending this to 14 bits, you would also have thousands. All right, so it's not hard to make this for loop a little bit bigger, and then you'll have to loop through more cases because with 14 bits, you got to shift everything through to the end. All right, so then the last thing you got to do, the very last stage, is you shift only, you don't dabble. Remember the whole point of dabbling was to think in advance, am I going to need to extend this to where it flows into the next BCD digit? Well, there's no need to dabble because we're not going to shift anymore after that. So the very last stage ends with a shift, okay, and from there, that lets you take the outputs and turn that into the outputs for the ports, okay? So let me pause the video because I forgot to paste that in, and let me just copy it. I'll just, hang on just a second. Okay, so at the end, this is what's missing. I forgot to paste this in from the example code. Rather than stopping and doing that, we'll just write it out. So once I have this, I need to assign the outputs. Okay, so what I know is that the hundreds are going to be the last shift register. So it's a shift reg 8. My writing's not very good. Okay. And that would be bits 19 through 16. You'd already looked at that. That's in the comments. Okay, so it makes sense that that would be the case. And then you also need to assign BCD tens and that's going to be shift reg. Which one? The 8th one, the very last stage. And which bits? 15 down to 12. Okay, and finally you need to assign BCD 1s. Okay, similar idea. We're looking at the last stage of the shift register that we developed for this problem. So it's the 8th stage. All right, and then this would be 11 down to 8. Okay, so remember the lower part of that is where the binary digit showed up. So the upper part of the shift register is where the data shows up for the BCD conversions. Okay, so look through this, read through this, make sure you understand it. I think if you can extend this to 14 bits, then that shows you have an understanding of how to make this code.